Hello, welcome back. This lesson is aimed to be just a quick explanation, a brief introduction to the concept of partial fractions decomposition. Partial fractions decomposition. So we first want to talk about what it means to break something down, to decompose something into partial fractions. So suppose we have an expression. Suppose we have a rational expression like this, like 3x plus 11 divided by x squared minus x minus 6. Suppose we have a rational expression, and I'm going to give away the answer here, show you what this thing breaks down into, and then I'll show you how to get there. So this thing can actually be broken down into 4 over x minus 3 minus 1 over x plus 2. And if you are seeing this for the first time, maybe in Algebra 2 or in pre-calculus, it may not be clear why this is useful. And for the time being, you're right. This kind of thing isn't really useful until you get into higher math applications. For example, when you take a class called Calculus 2, you'll learn how to take the integral of a function, which looks like this. And the integrals are notoriously tricky if you have some big expression with a lot of parts in it. By their very nature, they happen to be really difficult when you have it in a form like this. So it'll behoove us greatly to take this and break it up into 2 or more smaller parts, and then take the integral of that, and it just makes things so much easier, so much faster. So this method really just helps us build efficiency in solving advanced problems. Not only in calculus, if you go beyond calculus and you take a class called differential equations, you will learn how to take something called an inverse Laplace transform. Looks like something like this. And this is not a calculus video. This is not a differential equations video. So I'm not really going to I'm not going to get into what integrals and Laplace transforms really are, or what they do. We're going to focus on the process of decomposing expressions. So these are just a few examples on why it's really useful to know how to do this kind of thing. Best to have these kind of skills under your belt, so then by the time you're ready to start doing integrals and things of that nature, you'll be a pro at this already, and you'll be much more efficient than you would be otherwise. So we have our answer. We know we're supposed to get something like this. Let's explain how we get there. So a good place to start would be to factor our denominator if possible. And it looks like this one certainly is possible to factor. It would look like this. Our numerator stays the same, but beneath that we have x minus 3 times x plus 2. And in general, whenever you have something like this, something that breaks down into 2 linear factors, x minus 3 being a linear factor, x plus 2 being another linear factor, we can write it like this. We can write it as some integer a. I guess it doesn't have to be an integer. Let's just say a number a divided by our first factor plus another number b divided by our second power. So the tricky part is finding what these numbers are, finding a and then finding b. So that's always the place we want to start. After we set it up like this, our goal is to find the values that these numbers contain. We want to find a and b. So to start, we want to get rid of these denominators if possible. We want to make it so that instead of 3 rational expressions, we make them into just 3 normal expressions without any fractions. So there are a few different ways we can accomplish this. I think the most efficient way would be to find a common denominator. Move this aside for now. So it looks like our common denominator is going to be x minus 3 times x plus 2. So the a already has the x minus 3. All we need to do is multiply by x plus 2 over x plus 2. And in the case of our next term, we already have an x plus 2. So all we really need to do is multiply the top and the bottom both by x minus 3. So as you can see, we have 3 terms. They all have the same denominator, and the really nice thing about that is we can multiply all 3 of these by x plus 2 times x minus 3. We can multiply all 3 terms by the denominators effectively eliminating them completely. So we're going to do that right now, multiplying by the denominators and thus eliminating them entirely, leaving us with just normal expressions without any fractions. I'm going to move the a little bit closer, and then we have this last term right here. I'm going to move the b a little bit closer just to make sure it's clear that b is a coefficient in this case. So I might bring things a little close together. We don't really have that much space to work with, so I'll bring this in a little bit more. There we go. And we need a plus sign just to connect our two terms together. All right, so now that we've done that, we don't have any fractions. It's been made incredibly easy to find our constants now. It's much harder when we have fractions. Now that we've eliminated the fractions, it's much faster to find those values. So it really just boils down to picking a really good value for x, being strategic about what number you pick to be x, and deciding how it will help you decide and find out what a and b are. So for example, I want to make this into a 0. So I want to set x equal to -2. And I want to plug in -2 everywhere I see an x. We have 3 times -2 plus 11. And then if this x is -2, it makes this whole thing go to 0, just zeros the whole thing out. So we have 0 plus b -2 minus 3. So to simplify this, we have -6 plus 11, which gets us +5, equals -5b. So all we really need to do here is divide both sides by -5, and we found our first value. We found b. So b in this case is -1. So I like to just write these values right at the top corner as I find them. And then once I have that, I want to clear up this room over here, clear up some space so that we can find a, which is going to be a nearly identical process. So now we want to pick another strategic value for x that will allow us to find a. So we want to set x equal to 3, because only that value will make this entire b term go to 0. So x is 3. We have 3 times 3 plus 11 equals a times 3 plus 2 plus 0. Simplifying, we get 20 equals 5a. So then a is 4. So we've done it. We found our a, we found our b, we've done a vast majority of the hard work. We've done most of the heavy lifting. So the only thing left to do right now would be to go back to our original expression that we had before. We had a initially over x minus 3 and b over x plus 2. So substituting our values in, we get 4 over x minus 3 plus, it's actually going to be -1 in this case because b is a negative number. We're going to make it where it's going to be 4 over x minus 3 minus 1 over x plus 2. So that's really all there is to it. We're able to break down some big expression like this into 2 smaller, more manageable pieces.